MIPI controller with AXI controller. How the data is transmitted. So here I am explaining that just in the MIPI, the pixels, how the pixels are transmitted from transmitter side to receiver side. So this is the MIPI CSI controller. In this AXI signals, what is that signals? Clock signal, reset signal, active low reset signal, and then AXI clock. These are the AXI right channel signals. Okay, right channel signals, valid and ready is common for every channel because handshake is needed. And then AW address, that means right address channel address signal. Okay, 32-bit address signal. And then write data channel. In this write data, so what is that? Valid and ready. Ready is an output, valid is an input, and then write data is an input. And then your outputs are AXI be valid because valid signal should be outputted. That means ready. Response valid. Valid response is an output, ready is an input because slave is giving the ready signal, and then valid signal should be given by the master. Okay, so that means AXI right response valid, and then AXI right response ready signal. And then input signal clock and reset. This is the system clock and then system reset. Okay, AXI reset and then clock is also there. And also these are the MIPI signals, inputs and output signals. Okay, what is the input signal? Pixel data is the input, valid is an input, frame is an input, and then frame end is an input, line end is an input, and then output range is the busy is the controller signal. So that is the that means this controller signal should be tells you is that bus is idle or busy condition. Okay, these are the internal signals. What I am taking here, control registers. Actually, what is the control register purpose means you are doing the AXI protocol, right? In the AXI protocol, what type of data you are transferring, that controlling. Okay, how much data you need to send, what type of data you are sending, where you need to send, that control register will take care of that. And then control enable signal. After that, AXI W ready, and then that means right address channel ready signal, right data channel ready signal, and then valid signal, response valid signal. So these are all internal signals. Internal handshaking is needed to store some values and all these things. Okay, so and also AXI internal register is also there, so to store your address internally. Okay, so this is the AW ready signal, this is the actual signal, and then internal signal we are assigning that. That means driving whatever the AXI W ready signal is there, right? AW ready signal is there, that will be driving through this signal, AXI AW ready signal. Okay, so register is for storing purpose, but the storing value will be assigned to actual register value. And also valid signal is then ready signal. Okay, all signals are assigned here. So here write transaction I am doing that. In that write transaction, what it happens? Address phase, data phase, and response phase. Three phases are there. See, address phase, all the signals in during reset signal, all the signals are zero here. So it is in reset condition. If it is reset condition, all the signals are initialized to zero. Else begin. What it is doing? AXI W valid, AW valid, and AW ready. Both are high means so handshaking is happening properly. Then we are accepting the data. Then we need to store the AW address signal into this AXI address register signal. Okay, that signal is assigned to this AXI AW address signal. Okay, so in this way we will assign that. Okay, address is stored. After that, the AXI address is placed, and then we need to store some data, and then AXI W valid and AXI W ready. So both are one means you're storing some data. Here I'm storing some data is 00. Okay, this is the address range. Okay, address register is an 8-bit register. I'm storing 00 initially, and also during 00 I'm storing my data, right control register. That means AXAW data will be stored in register control. Register control is a 32-bit register. In that 32-bit data, we can store that. After that, valid and ready signal should be ready signal should be 0 and valid should be 1. Okay, because we have placed that valid signal. When you are getting the ready signal 1, so after reading the signal and then if data is accepted means okay, you are getting the ready signal. Okay, so stop condition, this is the stop condition. If it is 0 means your ready is valid, your data is accepted, and then it can stop the write transaction. And coming to the read transaction, what it is doing, AXA be valid and ready signal should be high. That means read address channel we need to keep that. Okay, valid signal should be 0 and ready signal should be 1. That is response is completed here, ready for next transaction. That means your slave is sending the response signal to your master, means okay, I have received the address and data, then I'm, if you want to send another data, I'm ready to receive the data, it will show that. Okay, it says that. And then this is the CDC, clock domain crossing, and this is for synchronizing purpose, because synchronization 1 and synchronization 2 will be stored in your register, because we are using two different clocks here, right? So AXA clock and then system clock. So that's why synchronization purpose we are using reset synchronization stage. See, during reset condition all signals are 0. Otherwise, synchronous should be register control, and then register control 1 should be stored in your register control sync registers. Okay, so then you are doing the controlling operation, enabling that controlling operation. You, based on that enable control enable signal, we are controlling that data. Okay, first frame start, frame start edge. How we are storing the frame start edge? This is the frame start edge delayed signal. So this is the delayed version. If during reset condition, this delayed signal should be 0. Otherwise, whatever the frame start signal is there, that will be stored in frame start delayed signal. Okay, so that means capturing the different cycles of values here. Okay, and also write frame edge. So whatever the frame edge, frame start and not the frame start delay. So then we can start your frame start edge. Okay. In same way, FSM. What is the FSM? Idle condition, frame start, line start, payload, line end, frame end. So this line start, frame start, line end, payload will be stored into this FSM. So how we are starting here? Register start launch here, start latch here. So during reset condition, your frame start is that edge condition we are storing here. Okay, this is the frame start edge. Okay, at that time my start is launched. Okay, so start latch is launched. Okay, I have started my condition, frame start is started. Then start, after that we are sending some frame, and then we are ending that frame. Okay, frame is started and frame is ended. Same similarly, state plus outputs we are mentioning here. During reset condition you are in idle condition. After that, releasing the reset condition, we are moving to the next state, that is the idle to busy condition. Okay, so idle, frame start, frame end, line start, line end, and pixel. So that is the FSM, right? So we are moving to the next state. That next state is what? So this is the next state. So in that current state, what is the value we are storing? Idle case. During the idle case, so the control enable and then start latch is both are one. We are moving to the next state, that is the frame send. Okay, send frame start. After reaching the frame start, then next state is send line start. So if it is line is started, then go for the payload. Okay, payload we need to send that. After the line start and payload, then we go for the line end and then frame end. Okay, so in this way we have sent the data to through using AXA protocol. Okay, now we can check the test bench here. Okay, so this is the interface. Okay, in the interface, what is the signals we are mentioning? So this is the interface signal: frame start, frame end, pixel valid, pixel data, line start, and busy signals. What are the MIPI signals are there? All the signals are interface signals we have placed here. And then package. In that package we are importing that. So we import UVM package, scope resolution star. Stick include UVM macros.sh. So what is the test we are doing here? We test in the under the UVM test. What is the test we have started? So just we are starting our test during in between the phase rise and drop objections. Okay. So then this is the test, and then top module we have placed that. What is the test we have placed here? This is the test. Okay, MIPI test under this test. So I'm starting my sequence. So starting my test. So sequence dot start environment agent dot sequencer. In the agent sequencer we are starting our sequence test. Okay. So what is the test here? In the test environment handle we need to create that. This is the custom constructor. So based on the custom constructor, we are calling the parent class, and then so we are calling super.new by using the base class we are calling here. Whatever the base test is there, that test I am calling here. And then environment handle is there, right? So in build phase, I have created the object for this by using create method. After that, in run phase, MIPI sequence item. This is the my sequence, and then that sequence I am starting here. Whatever the sequence we have there, for that we need to create the object by using create method. Okay, so this is the test, and then in the top module, what we are representing here. So top module, this is the my top signal, top module. So package importing. After that, clock and reset is initialized. After that initialization, we need to generate the clock. So clock equal to negation of clock, and also we generate the reset condition. Reset equal to 1 means it is in the reset condition after 50 seconds delay. So it is releasing the reset condition. And then with the interface signals, we have interface. Whatever the interface signals are there, we are instantiating the interface here. After that, dummy wires for DUT signals. That means whatever the pixel data, and then pixel valid, frame start, frame end, line start, line end. So all the signals we are fixing this dummy wires to store the values here. Okay, whatever the VF dot pixel dot data is there, that should be stored in pixel data, and then through virtual interface we are transferring the signals. And then this is my DUT instantiation. Whatever the signals are there, all the signals are instantiating here. And then after the instantiation we are setting the config db. Okay, config db null comma star and var comma var. So star represents the global representation. Okay, and then you will top dot set report velocity levels, that is the low condition. And then I'm running my MIPI test. This MIPI test pixel data is transmitting. Okay, so interface I have explained, and then test is also explained. After that, here sequence item. This sequence item, what we are executing, just this is the UVM package import, take include macros.sh in the MIPI transaction. So this is my base class. In the UVM sequence item, I am extending my transaction class. In the transaction, what is the number of pixels, and then pixels data. I'm randomizing. Okay, so I'm randomizing the pixels here, and then so constructor here, constructor for MIPI transaction, and calling the base transaction here. After that, I have written that number of transactions inside that 1 to 100. Then do the print method. So print method is for printing the sequences. Okay, so this sequence item we have executed. Sequence item we have executed with the sequence item. This is the sequence item. So same control, same design, and then we have executed that. This is sequence item or sequence item. MIPI transactions, pixel data, and then do compare. So module we have written. So just see how many pixels are transmitting for 10 transactions, because 1 to 10 transactions we have 1 to 100 inside that MIPI pixels are there. So and then transactions are we are inside that what is the condition we have taken, just see the transactions, number of transactions we have assigned, right? Pixel data is there, and then frame start interface signal is there. After that, this is the test. In this test, we are starting this test, so during the phase range and drop injections, and then what is the run test, MIPI test. This is the sequence item. In this, number of pixels it will be in between the 1 to 100. So that 1 to 100 pixels we are generating. See, number of pixels 1 to 100 we are getting 51, and then pixel data we are getting that. Okay, every time we are getting the pixels data. Okay, number of pixels will be 1 to 100 only we are getting that. Okay, so how many times we are repeating this CA test? So based on the repetition, 10 times we are repeating. So 10 different test cases are generating. Okay, that's what we are checking. And then same thing, MIPI AXI design. So this is so sequence item, you know, right? The sequence item is executed. Okay, so that is sequence item, and then interface, the test also executed. So environment just for connection, class registration, and then if this is your base class, and then extending that with environment, and then here class registration by using macros, and then in that agent we are having a sorry, in that environment we are having agent and scoreboard handles I have created. In build phase, I need to create the object for that by using create method. After that, in connect phase, I am connecting that agent dot monitor dot analysis port dot connect and scoreboard dot implementation port. So that is the connection. So environment is connected. In the agent, I am considering that active agent and passive agent. So both are considering if it is passive or active. If it is passive means if it is active means, so we need to take that UVM active, and then passive means it will be other condition it will consider that. See, in the agent what are the elements, driver, monitor, and then sequencer are there. Okay, those three handles. This is the class. The UVM agent is my base class, and MIPI agent my parent child class, and then class registration by using the UVM component details and registering my class with macros, and then handles I am creating. For that handles I need to create the object. Okay, so in that this is the constructor. So you will string name, using component parent name comma parent and function. By using super dot new method, I'm calling my base class. Okay, environment base agent base class I'm calling here, and then build method. In the build method what we are doing, so super dot build base, I'm calling my base class base build base, and then monitor I have created the object. Monitor equal to make MIPI monitor and type ID create monitor comma this. This is the component. That's why we are writing this. Okay, and then it is an active. We need sequencer and driver also. For that also we have created the object. Then connect phase, we are connecting. Which who are connecting here? Driver and sequencer. Okay. So driver dot sequence item port dot connect sequencer dot sequence item export. Okay. So this is the agent. And we have written the coverage also. What is the coverage? We have written each and every bit we have written number of pixels is taking, and then so pixel samples and then number of pixels we have considered in the class. After that coverage point, coverage name, options dot per instance 1. Okay, per instance equal to 1. That means each and every time one instance we need to place them. And then CP pixels equal to cover point number of pixels. this one bin and one feature I'm covering here, number of pixels. In that I have created 1 to 100, right? So 1 to 10 is the small, and then 1 to 11 to 50 is the medium, and then 51 to 100 is the large. I have segregated. So 1 to 100 pixels, 3 bins I have considered. And also we have a minimum value and maximum value, that means boundary conditions, and also some edge values, that means 10 is not covering, and then 11 is not covering. So 10 11 is not covering, that's why edge conditions we have considered. And also 50 is not covering, and 51 is also not covering. Then we have taken the other edge conditions. So then in number of pixels, all pixels will be covered here. And then sample pixels. Sample pixels means it is starting from 0 and ends with maximum value all f's. It is also low range. So 0012 to 000 ff, and also 00100 to 0 all f's, and then 01000 to all f's we have written there. Okay, so then transition coverage, that means FSM state is there, right? One state to another state, is that moving or not? 1 to 100 it is moving or not, or 100 to 1 it is moving or not, because we have taken that 1 and 100, that is the edge cases. Okay, that transition is happening or not. Then cross coverage, we are considering the pixels as well as pixels data. So that is my coverage code. In that constructor, we have written that coverage sampling. So CG equal to new, and then sampling the function here. So CG dot sample, and then I need to print the sampling data, pixels and data I'm printing here. This is my coverage. And then so driver code, in that driver code what we are writing here, so this is my class, and then extending from event driver, and then registering for the driver class to macros, and then what we are considering, interface, virtual interface. Why we are considering the virtual interface? We need to drive the stimulus to drive DUT, right? So through a virtual interface only we are driving, because your DUT is in static in nature and test bench is in dynamic in nature. So that's why we have virtual interface. And then function void build phase. In that build phase, what we are considering here, config DB. I'm getting the config DB from the top. In the top, we are setting the config DB. So this is used for this componency. If not using config DB, virtual memory interface, get this comma, this empty space means globally we are representing. And what is your string name? Virtual interface, VAX. And also value is also virtual interface. So if we are not getting this virtual interface, I am getting the fatal error here. And then task run phase, transaction handle I am created here. So for that I will create the object. Okay. So by using where we are creating here not written for the creation, and then sequence item code dot get next item, because in the transaction item we are this is the handshake mechanism between the sequencer and driver. Sequence item code dot get next item of transaction, and then through virtual interface I am passing the all values. Frame start equal to 1, frame start equal to 0 after the 1 clock edge. That means initially I have started, after 1 clock edge I have ended the frame start. And then during I'm waiting for the busy condition. If it is busy means, so wait for that, and then repeat number of transaction dot number of pixels, whatever the number of pixels we have taken, that many times it will be repeating. And then so I am assigning some data, so that data will be dollar random. So randomly I am considering any data, 24 bit I have considered, so that data is assigned any value. And then pixel valid equal to 1, data equal to data, pixel data equal to whatever the data we have, random data is assigned to pixel data. And then I'm pushing the data to queue. Okay, because one by one we are pushing, because pixels data is pushing onto the queue. By using pushback method, we are placing the data into that pixel data. Then we are displaying that whatever the pushing data, pixel data, and then q dot size and data. So whatever the data we have there, and then q data is there, that is displayed here. Then pixel data equal to 0. So line is ending is equals to 1, and frame is also ending. So then we are waiting for the busy and terminating the sequencer to driver handshake mechanism. Then driver code is ending. And then similarly monitor also. Monitor also same thing, class registration and even component parent, and then so class registration through macros, and then virtual interface I have written, and then UM analysis ports I have written, because these analysis ports are calling in scoreboard. So for monitoring, monitor is connected to scoreboard, that is the broadcasting purpose. For that broadcasting purpose, we are implementing the UM analysis ports. Okay, function new string name UN component parent super document in comma parent, and then we are getting that so AP equal to new of AP comma this. That means whatever the analysis ports is there, for that we need to create the object, and then memory we have created, and then in build phase I'm getting the config DB. Same thing, same we have written in the driver also. Even config DB, not even config DB, virtual interface, virtual memory interface, get this comma, empty space for global and VF comma VF. If you are not getting the config DB, then you will get the fatal error. So no virtual interface we are getting. The task country is event based, so I'm creating the handle for my transactions. After that, I'm starting my sequence here. So frame start is happening. I have created the object for my handle sequence item handle. After that, waiting for the busy condition. If IDX equal to 0 means I will do that. I'm waiting for the busy condition. Then what it happens here? So we are pushing the data into the queue. So that data we are considering. So that data I'm checking that. So is that happening properly or not? Then number of pixels should be assigned here. That transaction, whatever the transaction we are having by using right method, we are assigning in scoreboard. Okay, this is the scoreboard code. MIPI scoreboard extends from UM scoreboard to class registration of my scoreboard through using macros, and then in here UM analysis ports. This is here implementation ports is there now, so here export. So that export implementation is I am using my handle. To implement in the function new constructor, I am creating the object for the implementation ports. Okay, and then function write method, if count is matching, then we go for that. So statistics we are taking that, and then for each the pixel dot transaction dot pixel data of QI. So whatever the Q data we are having, that Q data, what the expected data is the Q of I. Okay, that data we have stored, and then actual data same pixel data Q of I, that should be assigned to actual. Okay, so this is from DUT. So DUT we are getting the pixel data Q of I, and then that should be assigned to actual data, and then we are displaying that actual expected data and actual data. If the expected and actual both are equal, my test case is passing, and then I'm getting the matched condition. Otherwise mismatch will be happening. Okay, then I'm showing the match condition or mismatch condition. If mismatch, final result should be fail. If it is matched, and then final should be passed. Okay, that is the scoreboard. Sequencer, you know, right? Sequencer is the just the class registration and then custom constructor. That's it. And then package we have written already. So in that package, whatever the transactions are, transaction sequence, driver, agent, environment test, whatever the classes we have, all the classes we will implement in the package. Okay, so agent we have covered. Sequence. So what is the sequence we have written here? So class registration, and then class extension, and then registration of my class, and then so custom constructor we need to write anywhere. Okay, after that task body method. In the task body method, what we are writing here, so creating the handle of my sequence item, and then repeat of three times it is repeating, and then start item, asset, randomize, after that finish item, create, start item, randomize, and finish item. Through this, my transaction items, whatever the transaction items are there, all the transactions items are, it will be randomized. Okay, so this is all about your test bench code, driver, monitor, sequence, package, code, sequencer, coverage, agent, environment, test, and then sequence item top. Okay, so we run this. Just we are seeing the sequence items. It is is running or not. So we need to check the test. Okay, one test is passed and then test done is one and then finish item. So EVM info 4 messages we have seen. Okay, so this is the MIPI test case.